Mass and energy form the basis of our universe. For years, physicists tried hard to arrive at a direct relationship between these two entities. Eventually, in 1905, Albert Einstein claimed that mass and energy are the same things. He came up with his revolutionary equation that changed the existing perception of the universe. I'm talking about none other than E equals mc squared. An equation that showed how mass and energy are interconvertible. We see an ample number of examples of mass getting converted into energy. It wouldn't be wrong if I say that this process is the fundamental basis of our living. How? Well, you would be surprised to know that with every passing second, the Sun is converting 4.26 million metric tons of its mass to produce the equivalent of 384.6 septillion watts of energy, the same energy which is fueling our life cycle along with other processes on the Earth. Although we've witnessed real-world examples beautifully portraying the conversion of mass to energy, what about the reverse process? Have we ever seen energy converted to matter? Well, the answer is yes. In a recent breakthrough, scientists have produced matter from photons, which is the quanta of electromagnetic energy, in a stunning demonstration at the Brookhaven National Laboratory. Physicists are claiming to have created matter from pure energy, and that too, for the very first time. It is a known fact that whenever a particle and its antiparticle collide, they annihilate, thereby releasing a small amount of energy. So following this, E equals mc squared equation says that the reverse process is also possible. This means that if you smash two sufficiently energetic photons into each other, then we should be able to create matter in the form of a particle and its antiparticle. Precisely, this process is known as the Bright-Wheeler process. This process was first described by American physicists Gregory Bright and John Wheeler in 1934. But it has been one of the most difficult ones to demonstrate experimentally. The reason is simple. For photons to produce matter, the colliding photons need to be highly energetic gamma rays, and to produce such energetic gamma ray photons, we need gamma ray lasers. But mankind has not yet been able to make such gamma ray lasers. So scientists went for an alternative. While proposing the process, Bright and Wheeler had suggested that the experimental demonstration can also be performed by accelerating heavy ions instead of directly using high-energy photons. And this is exactly what was done in the recent demonstration. So instead of accelerating energetic photons directly, the researchers sped up two positively charged ions in a big loop, and then they sent them past each other in a near collision. These ions are charged particles that move very close to the speed of light. This means that each of them also carries an electromagnetic field associated with them. Inside this electromagnetic field, there are many not so real but virtual photons that travel with the ion like a cloud. Now you might be wondering, what are these so-called virtual particles? Well, these particles pop into existence only briefly, as long as the disturbances in the fields exist between real particles. They don't have the same masses as their real counterparts. So unlike the real photons that have no rest mass, virtual photons do have a mass. Now coming to the experiment, when the ions zip past each other in a near miss, their clouds of virtual photons moved so fast that they acted as if they were real. Eventually, the real acting virtual particles collided and produced a much real electron-positron pair. But wait, the photons used here are virtual. And for this demonstration to be a true observation of the Bright-Wheeler process, the physicists had to make sure that their virtual photons were behaving like the real ones or not. So to check the credibility of the virtual photons' behavior, physicists detected and analyzed the angles between more than 6,000 electron-positron pairs produced by their experiment. When two real particles collide, the secondary products are produced at different angles than if they were made by two virtual particles. But in this specific experiment, secondary products bounced off at the same angles as secondary products from real particles would do. This means that the particles they were analyzing were behaving as if they were made by a real interaction. Moreover, the researchers also measured the energy and the distribution of mass of the systems and found them to be consistent with theory calculations that were expected to happen with real photons. In this way, researchers have successfully demonstrated the Bright-Wheeler process after decades of its proposed existence. But despite the success, one cannot ignore the fact that the photons used in the experiment are still undeniably virtual. Although this raises some questions on whether this experiment was a true demonstration of the Bright-Wheeler process, still, it is an important first step until we have lasers that are powerful enough to demonstrate the process with real photons. If you're interested in studying astrophysics at home, make sure to check out our Basics of Astrophysics series, the link to which is given in the description. This series explains everything at the most fundamental level, from the EM spectrum to telescopes, and from the birth of stars to the formation of black holes and galaxies.